All right, we're going to define congruence modulo m, and then you're going to do some examples here. So the setup is the following. We're going to take two integers in z. So in the context of the previous videos, this is kind of our set S that we're going to define an equivalence relation on. And then we're going to take a natural number, and that natural number we want to be bigger than 1. You could take 1, but 1 leads you to something kind of non-interesting. So our natural number is going to be bigger than 1, and this kind of, it's not exactly true, but it's the reason why it's uninteresting when m is bigger than 1 is somewhat related to the reason why, or sorry, when m is equal to 1, it's somewhat related to why we don't want our primes to include 1. It's not exactly true, but it's morally true. Okay, so this is the setup. We want to say what it means for A and B to be related in this relation, and this relation is called congruence modulo M. So we say that A and B are congruent modulo M. Okay, so this is what we're defining here, this notion of congruence modulo this natural number M that we're fixing at the outset. If M divides A minus B, and we write any number of things. You can write A is congruent to B modulo M. You can write A is congruent to B. Sometimes people like to put this in quotes. We write A congruent sub M to B. This is my favorite because it's the least amount of writing, and mathematicians generally like the least amount of writing. At least I do. All of these mean the same thing. All of these are equivalent to saying M divides the difference between A and B. So let's keep that definition up there. And I'll do the first two parts of this activity, and then you'll do the other ones. So we want to justify the congruences. 1 is going to be 18 is congruent to 6 mod 12, and 2, well, let's do 1 first in the interest of space because I don't want to scroll off this. Okay, when we write 18 is congruent to 6 mod 12, what we're saying is that 12 should divide 18 minus 6. And that statement itself is the same as saying 12 divides 12, which is certainly true. Every number divides itself. Okay, so that's us justifying the congruence 18 is congruent to 6 mod 12. Let's do 2. If 2 is 47 should be congruent, and I'll use some different notation here, mod 13 to 8. So this is saying that 13 divides 47 minus 8, and that's saying that 13 divides, let's see, 47 minus 8 is 39. And this is certainly true because 39 is 3 times 13. Great, so it definitely divides it. And so with 3, 4, and 5 from our book, I want you to do a similar thing and justify 71 is congruent mod 5 to 1. 21 is congruent to negative 1 mod 11. And 24 is congruent to 0 modulo 6. And I've just used different ways of writing the same thing, again, because depending on who you talk to, they write different things.